Yeah, thanks to Irina and Yon for giving amazing talks. Now I don't have to talk about this first slide because it's about the X-ray and the H alpha. I mean, this is O2, but similar temperature gas in the centers of galaxy clusters. So multiphase gas is seen, and we have discussed so much about its properties. So I will talk about one particular channel of formation of these cold clouds, which is through thermal instability. Okay. Right. So, as being a theorist, I am worried about time scales. What are the different time scales that we are concerned about? First is the cooling time, which is simply the ratio of the internal energy to the cooling rate, and that's given by this formula. And then the free fall time, which is basically the time it takes for a cool clump to fall towards the center by some particular scale height. And the g that you see is like the acceleration due to gravity. Now, the turbulent mixing time is given by, if you have some characteristic length scale L, then the velocity on that scale VL, and that's your turbulent mixing time. So if you have a small region that is trying to cool, either it can be put back into pressure equilibrium under a free fall time, or turbulent mixing can mix it up with the surrounding before it undergoes runaway cooling. And then there's another time scale which comes from some linear stability analysis, which is rate of growth of thermal instability, and that is sort of proportional to the cooling time, but it depends on what exact model of heating you are using, whether it is density dependent, whether it is volume heating. So it depends on some of these. But for my talk, it's basically just 3.33 times T cool. So for this talk, right? So short cooling time means cold gas is more likely to come out of the hot phase, whereas shorter T free fall and T mix, because they are trying to prevent this cold gas from forming, they will prevent condensation. Right. So also, I'm not the first person to talk about this. This work has been was probably started like 12 or 15 years ago, first by Mike McCourt and Pratik Sharma, and they came up with this criterion, which many of you might know, is that T cool by T free fall being less than or equal to 10, and then you see multiphase gas in galaxy cluster. So galaxy cluster, circumgalactic medium, it applies to many of them. Max Gaspari in 2018 came up with a different criterion, which was saying it's the ratio of the cooling time to mixing time that matters, and if cooling time is less than the mixing time, then you will form multiphase gas in your system. And then there are many different idealized simulations. One is by Prakriti Pal Chaudhary. So in these idealized simulations, what she did is she took a local box of the ICM and initialized some density perturbations in it. And then she watched whether they are growing and going on to form multiphase gas, or whether those densities just die down. And what she found is that the threshold density perturbation that you need for for multiphase condensation to happen actually increases as you increase this TTI by T free fall. So if you are generating very large density fluctuations, then those dense regions can cool down and then give you multiphase gas. So the idea is it's not a global criterion, but rather it's a local criterion, that locally your gas can become high density and cool fast. And then Mark Voigt also came up with this theory, which says T cool by T free fall should be less than an exponential function of C times the amplitude fluctuations of entropy. You can also think of this as density, because the fluctuations are mostly isobaric, so there will just this constant C will change. And here the idea is that if your density distribution is log normal in a turbulent flow, and then if you only care about the high density part of your density PDF, then those dense regions are going to cool fast, and you take care of that log normal distribution by including this exponential factor here. Now, what do observations say? So Valeria did this amazing work a few years ago now, in which they were finding is that I think these square regions indicate where we find multiphase gas in many different galaxy clusters, and they were finding, you can see on the left is T cool by T free fall being between 10 to 20. They also looked at T cool by T eddy, and they were also finding this to be around 0.5 to 1, right? So the question that and I think Mark Voigt and Megan had this paper where they looked at H alpha emission in the accept sample of clusters, and they were that the T cool by T free fall in those was between 5 to 20. So this seems to be occurring in both observations, and theorists were also predicting it. And my question was, what is actually more important? Is it T free fall or T mix? And I basically designed some idealized experiments to study this. So yeah, these are our simulations. We essentially have a stratified box of size like 40 kiloparsec, and the gravity is along the negative z direction, which is pointing downwards here. And yeah, these are just a local simulation, small patch of the ICM, and we generate fluctuations through turbulence, and those high density regions cool very fast, and then they form this multi-phase gas. Then that cold gas sort of mixes with its surroundings, and then it makes more cold gas. And because these are denser than their surrounding, they're not in hydrostatic equilibrium anymore, so they fall down to the bottom of the box because there is gravity, right? So we drive turbulence on 20 kiloparsec scales. We have done both compressive, solenoidal, mixed, all different drivings. These are the resolutions. This particular simulation I'm showing is like 1024 square times 1536. So we have some buffer regions which I'm not showing to take care of boundary conditions along z direction. So if you're trying a hydrostatic box, the boundary conditions can be a bit tricky along the z direction. Right. So this is the starting temperature and density, and yeah, our periodic boundary conditions along x and y. Okay. Now there is another magic heating term in these simulations, which essentially what it does is in each shell of these simulations, we calculate what's the total turbulent forcing power, and then we calculate the total radiative cooling rate. And to prevent the entire simulation from undergoing a global collapse, we add some heat to each shell. So it sort of magically replenishes the heat, the cooling, the energy that is lost due to cooling in terms of this magic heating term. Okay. And this is partly also because when in our simulations, if we try to use the velocity measurements for the Perseus cluster to generate our turbulent forcing power and match the velocities, then we were unable to match the radiative cooling in these simulations. So we had to add this extra heating term to prevent a collapse. Okay, so now we did some simulations. In this case, the only difference between these two is that the stronger gravity in the left runs. So here we are looking at density, this temperature, and these are some time scales. Right. So you can see that initially the T free fall is smaller for this one compared to this one. T mix is very large, but it will come down as we start driving turbulence. And this is sort of the thermal instability time scale. You see it has a steeper gradient here because there's a stronger density gradient. Now, when we start simulating turbulence, another thing to notice is that because this has a high density gradient, when turbulence starts mixing this up, the mean density sort of goes up a bit compared to the right one. So that's one small difference. And these are sort of the average ratios of these two important ones. So there's TTI by T free fall is like 4 and 2, whereas TTI by T mix is like 6 and 7. And what we will see is actually the run with stronger gravity forms multi-phase gas in this case, which may be a bit counterintuitive to people who have thought of just the classic T cool by T free fall relation. So you see that the left one forms cold gas, and then the thermal instability timescale grows a lot more. Now the amount of density fluctuations we have will not be able to generate cold gas in this system anymore. So after this cold gas forms and drains down, it raises the thermal instability timescale of the system. Right, and in the right case, what we find is, the mixing time is actually the more important case here, and it's able to prevent thermal instability from happening. So our main takeaway from this was, we see which one is larger, TTI by T free fall or TTI by T mix, and that basically, the larger of the two tells us which one is going to form multi-phase gas or not. So if we go back to the previous studies which did not have this driven turbulence, and the mixing time due to turbulence was not very important, so that's sort of this case. You can see that the turbulent mixing time is much larger than the other two time scales. And here we'll see something very different happening. We'll see that the right one will actually form multi-phase gas in maybe around 0.2 more gigayears, right? So you see there are some cold gas sort of starts forming there. And then that sort of raises the TTI by T TTI by T free fall and TTI by T mix. And after this, after the cold gas rains down, this will not form multiphase gas anymore. So here, TTI by T free fall was larger, so that was determining the criterion for forming multiphase gas in this simulation. Now we put in compressive driving because that's also something that can happen in galaxy clusters. The thing is, this can, oops, I'm pressing the pointer, right. So here we generate very large density fluctuations with the same RMS velocity. Okay, and here we see cold gas forms in both simulations because the density fluctuations are too large and neither the free fall time scale or the mixing time scale are short enough to prevent these fluctuations from undergoing runaway cooling. Okay, this is simply because we have very large density fluctuations here. Now, we are trying to come up with a condensation criterion which can separate our simulations that form multiphase gas from the simulations that do not form multiphase gas. So on the left here, you are seeing minimum of TTI by T free fall, and sigma is sort of tells you the amplitude of density fluctuations. Okay. Now, this is our attempt at getting a condensation criterion. So I want all these filled points to be below this curve and all the unfilled points to be above on this left side. Okay. But what's happening is that there are two runs with weak gravity for which this condensation criterion doesn't work. And this is sort of very close to what Mark Voigt's proposal was in the 2021 paper. So only a couple of simulations don't work very well. Whereas if we take TTI by T mix, so only thing I've changed is T mix in the denominator here. Here we see that these two simulations are now above this new condensation criteria. It's just slightly rescaled. It's an empirical fit. Okay, but now we see these two simulations which had very weak mixing but strong gravity, and now they are below the condensation curve, and I also don't want that. So what I do is I build a joint one in which the minimum of T mix or T free fall. So which one is smaller? Whichever one is smaller, I take that in the denominator. And now both of these sets which are not agreeing in the previous two plots, now they are all above this condensation criterion, and it sort of has this form in which there's an exponential dependence on the amplitude of density fluctuations. Right, now just switching topics slightly, talking about how well do our predictions for density fluctuations in non-radiative simulations, so simulations without cooling, work for simulations with cooling. Now, this is a relation that we predicted from our stratified turbulence simulations without cooling, and we found that many simulations actually work well for the fluctuations, but there are some which form cold gas, and they show excess fluctuations simply because there is this dense gas is collapsing onto form this cold gas, and then we find larger density fluctuations in those regions. We found that it's possible to trace this using this Mach. If we use a Mach compressive, then it can predict these ones. So this is a relation from Constantine et al. In 2012. But somehow it doesn't work for these runs. So this is a bit confusing for me why it doesn't work, but we can discuss about it more. Right. So yeah, basically when you have cooling, then there are some additional density fluctuations. Now, okay, how much time do I have?
7 minutes.
Oh, great. Right. So now I was showing you all idealized turbulence driving on like 20 kiloparsec scales. What if we include some more realistic turbulence driving? So this is sort of more recently what I've been doing. And we had this paper out just a couple of weeks ago. Here we are looking at type 1a supernovae in massive elliptical galaxies. And the motivation for doing that is these galaxies sort of have very uniform X-ray emission, and they look very uniform in near infrared. In this case, we can see that the radioactivity is not very strong. It's not interacting with the entire ISM. But if we calculate the cooling time in the center, it's around between 10 to 100 million years in the central kiloparsec. But if we take the stellar distribution and take some normalization for calculating the type 1a supernovae rate, what we find is the heating due to supernovae is almost sufficient to match the cooling in this NGC 4649. This is just an example. in the inner regions. Of course, the stellar mass distribution falls up faster than the gas distribution, so this will not work on larger scales. This will also not work for more massive clusters where the central density is much larger. So this will work for intermediate mass elliptical galaxies, I would say, not the big ones like M87. Okay, so this is sort of our motivation, and again we did some very similar simulations. Just instead of driving turbulence on large scales, now we are putting in energy through these supernovae, and they are also triggering multi-phase condensation. So we have simulations of a small 1 kiloparsec cube of the ISM using the new GPU code Athena K. It's very fast. Try using it. Right, and different strengths of stratification, different initial density, different supernova rates. So that inherently gives us different T free fall, T cool, and T mix, all of these. Now what we found here is that we again went for the same multi-phase condensation criteria. This is a very similar curve just for the supernova driving instead of the idealized turbulence driving that I was showing before. Okay, again the filled points are the ones that form multi-phase gas. Unfilled ones remain single phase throughout the simulation. So what we find is, in this case, TTI by T free fall actually works well for all our simulations. We needed to rescale it slightly. It's 0.6 times exponential of 6. So it's like smaller by a factor of 0.6. But some of that could be due to rescaling of the thermal instability time scale, which is different for supernova heating compared to the magic heating that we were using before. Okay. For TTI by T mix, what we found was there was only one simulation which was pretty close to the boundary, and it was not forming multi-phase gas. So yeah, this was a run with stronger gravity. It had a strong scale height. It had a strong density scale height. So I think that's what was causing it to not form multi-phase gas. Now, when we looked at the combined criterion, that also sort of works, but it's much steeper for these. It's much steeper for these for the runs with supernova driving. I think in this case, TTI by T free fall was actually working the best, in my opinion, because in this case, yeah, there are some that are lying on the line a bit close, but yeah, this was working the best. We also looked at density fluctuations with Mach number in these in the ISM of these ellipticals, and what we found was they are actually pretty large, really large density fluctuations. The B parameter which Christoph introduced in yesterday's talk, I think this is B square, is close to 50. It's actually very large density fluctuations simply because we have these hot ellipticals expanding and mixing with the surroundings. And it's not just due to turbulence, I think it's also due to the heating of the ISM, and that was driving this density fluctuations to be extremely large. We tried scaling it with the compressive Mach number again, and I think the scatter is a bit less compared to before, but we often see these kind of vertical motions of a particular simulation. It starts around here and then goes up here. I think that's associated with cooling. So when you have some over-dense gas regions that are sort of trying to collapse, they don't follow this scaling relation very well. They sort of go more at an angle to it, and they form multi-phase gas. So it wasn't always working. What we found was like this was sort of acting like a lower limit of the density fluctuations, and this was like a right. And can we observe this actually? So we checked whether these supernova bubbles that are generated by this, whether they can be observed in M87, but we found they're like for M87, the size of the cavities where will generate, they are like half the resolution limit of Chandra. So they won't be observed, but maybe in future extra-missions, we may be able to detect them. So that's something, that can be done in the future. Okay, so conclusions, multi-phase condensation is supposed to be a local phenomenon, and it's more likely if you have large density fluctuations or a short cooling time, or either of these T free fall or T mix are long. Then we can have multi-phase condensation, and we came up with this new criterion which sort of combined the two things that people were talking about in theory over the past few years. And it works for both idealized turbulence and supernova-driven turbulence. Then density Mach relations, we find much larger density fluctuations when we have radiative cooling.
All right, if people have questions, please go over to the side. Start with one over here.
Thanks. Very nice talk, thank you. I want to dig a little bit into the magic heating function. In linear theory of thermal instability, of course, the importance is attached to the temperature dependence of the net cooling, so you're cooling minus heating.
Yes.
And so a lot of attention is paid to the detailed cooling mechanisms, but not so much to the actual heating physics. You might imagine microphysics, of the microphysics of the actual dissipation process of how the energy is dissipated, changing at the local level the dependence of the heating on the density, the temperature, right. the plasma beta, for example. Do you feel that there's a possibility of that qualitatively changing the picture away from what you currently have? Or have you done any work to sort of experiment on different heating prescriptions?
So I had done this, but not in the stratified case. But I remember in Pratik's paper that they had the thermal instability growth time scale actually has, so let's say if the heating depends on density as rho to the power alpha, then that alpha actually goes in the denominator of when you convert from T cold to TTI, which is the time scale of thermal instability growth. So the temperature dependence of the cooling in the denominator, and you also have alpha in the denominator. So it already goes in when you are calculating the thermal instability growth rate. So we can do both volume dependent heating and density dependent heating. Or like
there's at least the prospect for qualitatively changing the result. I mean, for example, going back to Balbus in the 90s, he showed that if you make some very strict assumptions about both the cooling and the heating, you just make them purely dependent on local state variables, then a system that is spatial stable will be thermally stable, at least locally, linearly.
Right.
There's a prospect for qualitative.
I think it will definitely, yeah. I think it will change because, right. So I was showing, yeah, right. TTI by T free fall was the criterion that I was showing. So if we are considering T cool by T free fall, that will be different for these two systems, right? What I'm saying is TTI already tries to take care of the thermal instability growth time scale. Yeah. Whereas if you just use T cool by T free fall, then it will be different for these two systems.
Okay. I mean, I'll end with one comment. One quick warning about observational checks of T cool over T free fall is the observed quantities you put in to calculate that. You can actually also phrase, for example, as a critical entropy, or you can actually also phrase as the balance of thermal conduction with so the actual quantity, the interpretation of that bunch of observables as a T cool over T free fall may not be unique. There's one warning there.
Thank you.
My question is related to the previous question, and for a while people were thinking that in, for example, intercluster media, we have some particular instabilities, and the pattern of these instabilities will determine the outcome. Could I understand your work is that the final state is determined by the generation of turbulence by these instabilities and the feedback on these instabilities by turbulence, which does not allow the formation of any regular patterns that earlier researchers suggested.
So I think one of the differences is that we don't seed any density perturbations by hand to see what instabilities develop. We drive turbulence with observed gas velocities of like 200, 300 kilometers per second, and then we see what's happening to the system after that, which one is developing, right? We do see, like, if we, for example, if we increase the strength of gravity, we are seeing that, that gravity is stopping these density fluctuations from undergoing runaway cooling. We are not, see, I remember many of the linear instability simulations before used to put in like a flat spectrum of density fluctuations. And here the difference is that due to turbulence driving, the density fluctuations are on the largest scales of the system, and they will, if you think that density is a passive scalar, then it will follow the velocity power spectrum across all the scales. So that's one key difference between these two. So,
okay, can I reformulate in this case? If you just start with the instability, you just no turbulence driving initially, and then instabilities usually develop turbulence.
yes, so
And
that's sort of what we
is it possible to say that turbulence is provides the limits for the development of these instabilities?
Right. So I think that's sort of partly true, at least for this system. What we found is, although we did not initially see very strong turbulence, this was very weak. You can see it's like 20 kilometers per second, which is really weak compared to what is observed in the ICM. But we see that, these instabilities still go on in this right simulation where the gravity was not strong enough. And you see that because of these instabilities, it also drives this mixing time close to the free fall time, because as these clumps are falling, they are driving turbulence in the ICM, simply as the clouds fall through.
Okay.
Great. Let me ask Megan's question before we stop. So do these cold clouds you're forming look at all like the H-alpha filaments? And if not, have you thought about maybe including magnetic fields, which might help?
Right. I think with regards to magnetic fields, I think there was a great work involving Swocking G and Pengo a few years ago. Yeah, maybe we can talk more about that in the discussion. With regards to following these cold filaments very well, I think there's still one thing that is missing here. Maybe I will find it in my additional slides, is that we are not resolving the cooling length in the system, because the system size is very high. It's like 40 kiloparsec. If I want to resolve the cooling length, I have to increase my resolution by a huge factor. It's more possible in the latter simulations that I showed, because there we were only 1 kiloparsec in size. So yes, so this is the plot that I wanted to show. Often people say that, if we are looking at this temperature density phase diagram, then cold and hot gas, often people are finding it to be isobaric, right? But in this case, they are not isobaric. This is the isobaric line, so cold gas should have probably gone through here, but we stopped resolving the cooling length around here. So that's one issue. But for the newer simulations, if I still have that plot, we are actually resolving the cooling time almost down till here. So it's not that far off. So maybe then we can study, because otherwise we may have some artificial clumping, more averaging, all of those averaging leading to more cold gas formation. So we didn't talk about much about what happens after the cold condensation happens, because before the cold gas condensation happens, we are dominated by what is happening on the large scale. But once you form cold gas and it starts collapsing, then we need to resolve all the scales so that I can confidently talk about how that cold gas is going to behave and fall down, its dynamics, all of that.
Fantastic. Okay, great. Let's thank all the speakers and get some coffee.